Okay, good afternoon and welcome back to this last talk of the first day of this workshop before the upper and poster session. So it's a great pleasure to introduce our next speaker, Karen Willcox. Karen is a professor in aerospace engineering and engineering mechanics at the University of Texas at Austin, and she's the director of the Oden Institute for Computational Engineering and Sciences, as well as associate vice president for research. And she moved there in 2018, and before that she has spent 17 years as professor at MIT, where she served also as founding co-director of the MIT Center for Computational Engineering and associate head for the MIT Department of Aeronautics and Astronautics. She's very well known for her works on reduced order modeling, multi-fidelity methods, more recently digital twins, and many more things. And she received a lot of awards and honors. In particular, she's fellow of the Siam Society and for the American Institute for Aeronautics and Astronautics. And without a further delay, we welcome Karen Willcox for this talk of today.
Great. Thank you very much, Fabio. It's great to be here. So I hate standing still. If you've ever seen me speak before, you know I hate to stand still, but I'm under strict instructions to stay here so that the camera and the mics can pick me up. Anyway, it's really great to be here, and it's great to be giving a talk to three-dimensional human beings instead of 2D human beings. I had 3 events all nicely organized in Europe back-to-back, and one by one they started to get postponed, but I was really happy that this one was still live. So as Fabio said, I'm going to talk to you about some of the work in my group that we've been doing in digital twins. And before I start, I want to acknowledge our collaborators, and primarily I really want to acknowledge, whoops, it's the wrong button, there we go. Michael Captain, who was my PhD student at MIT. Michael finished his PhD in June. He's now a postdoc with me at the Oden Institute, and most of what you're going to see today is Michael's PhD work. We also collaborate with Axelos, a local small company, particularly with David Knezevic, the CTO of Axelos. You'll see some of Axelos's reduced order modeling work underpinning our digital twins. We work with Jasara, Jacob Pretorius, the CTO of Jasara. They did a custom sensor suite for our aircraft hardware that you'll see. And then Stephanie Salinger was another one of my students. She was a master's student at UT Austin. She's now working at Lockheed Martin. So with that, we're here these 2 days to talk about digital twins, and we've had a number of really interesting and I think varied talks on digital twins today. Of course, there are many different definitions of a digital twin. The one that I'm showing you here is one that was published at the end of last year by ARAA, as the American Institute of Aeronautics and Astronautics, an institute position paper. And this definition was the result of a lot of community working groups and discussions. Of course, all definitions are imperfect, but I like this one, and I think we've heard these themes throughout the day because it really calls attention to me for what makes a digital twin as opposed to just a powerful set of models and simulations as we've been doing for decades. And in particular, again, as we've heard all day, the thought that, first of all, the digital twin is personalized, that it's really focused towards an individual or towards a unique physical asset. Second, that the digital twin is a living computational model, so it's not a static model, but rather one that's dynamically updated with data from the physical twin and follows the physical twin throughout its life cycle. And then third, very importantly, when it comes to the methods, that the digital twin really is about driving decisions. And so, again, in terms of thinking about what's different with the digital twin paradigm, really thinking about the way we integrate models, data, and decisions that I think goes far beyond what traditionally the modeling and simulation community have done. So it's a really exciting concept. You may know that the digital twin idea has its roots in aerospace engineering, and as you heard in the introduction, I'm an aerospace engineer by training. The term digital twin was coined around 2010 in some work that was being done by NASA and by the US Air Force. But the idea, and I'm not sure how well you can see those, the lights are a little bright, but the idea is much older. And if you haven't read the blog post by Stephen Ferguson from Siemens, I really encourage you to read it, because I think it's a really nice post that highlights the historical perspectives on digital twins, and in particular that many people point to the Apollo program as being the first place as where digital twins were put into practice, even if they weren't then called digital twins. And in particular, NASA would keep digital simulators on the ground in Houston that would mimic the missions of the spacecraft that were being launched into space. And of course, this is something that became very famous in the Apollo 13 crisis. I'm not sure, I know the audience gets younger and younger, but maybe the older ones among us have seen the movie, where the spacecraft suffered an explosion, got stranded up in space, and the story goes that NASA took data from the crippled spacecraft stuck up in space, fed the data into the digital simulator back on the ground in Houston, dynamically updated the simulator, and then used this now updated simulator mimicking the real conditions to run the scenarios and to drive the decision-making that ultimately brought the astronauts back home. So I think this historical perspective is really important because, of course, we can always learn from history. Think about when this was taking place, 1970, just over 50 years ago. Think about what kinds of sensors they had on board, just how much data was their data. The data was probably big to them. Think about the sophistication of the models, and think about the computing power that was available. And I think this is a really good reminder that a digital twin does not have to be an exquisite replica of a system down to the finest detail, down to the molecular level in order to be useful. Now, of course, the examples that we've seen today, we're really starting to push the frontiers in terms of the sophistication of the models and the amount of data that we have available to drive decision-making in really complex systems. But again, this Apollo example is a reminder that models and data can be imperfect, computing power can be limited, but nonetheless, this paradigm of combining models and data can really bring value to decisions. So 50 years later, we now have a great name for this concept. I love the name because for the first time in my life, my family understand what I do. And in fact, when my 6-year-old daughter mimics me, she says, "Hi, I'm Karen Willcox, and I'm here to build digital twins for you." So, when a 6-year-old can get it, it finally maybe makes computational science a little bit more accessible to society, which is something that I desperately think we need. We have a great name, and what's more, this idea of digital twins has moved out of aerospace engineering. It's across, of course, all different kinds of engineering, and then even beyond engineering. Again, we've heard talks today about the power and the potential of digital twins in medicine, about the power and the potential of digital twins when it comes to the natural world around us, and in particular for driving key decisions, for example, around climate change. So lots of successes, a lot of really exciting work going on, and of course we can look out into the media, into various companies, and we can see digital twins being deployed. I think it's fair to say that we're still in the early stages of digital twin technology, and in many ways I believe we're still in what I would call an expert-driven phase, where in order to create a digital twin for your system, it's kind of like you start over every time, where you need to look at your system, look at the models, look at the data, do a lot of integration to bring them together, and also inject a lot of expertise. And I sometimes draw an analogy with the early days of the finite element method, or the early days of computational fluid dynamics. So back in the last century, when I was a graduate student, when you came into a lab to do a PhD in computational engineering, the first thing you did was write your own computational fluid dynamics solver, or write your own finite element code. Those days are gone because we now have robust, reliable, broadly accessible foundations on which we can build. And so again, to draw that analogy, I think that's kind of where we are at digital with digital twins. So this is one of the questions that my group asks is, what will it take? What does it take to move from that expert-driven custom phase to really having these accessible, robust digital twin implementations at scale? And of course, it takes many things. And I don't want to underemphasize the importance of things like software and standards and partnerships between universities and companies. But one thing that sometimes gets overlooked is the rigorous and scalable mathematical foundations. One of the reasons we have amazing finite element software that you can buy and literally push a button on is because of some of the theorems that were proved over the last decades that really made the methods, gave them a very, very strong foundation. So this is where I see a big role for academia, a big role particularly for the computational mathematics and the computational science communities to really think about the mathematical and the computational foundations that will make digital twins robust, will make them sort of accessible, and also will let them go to scale. I was really happy to hear, where's Eleni? She's sitting somewhere at the back. She already said this today, and then we heard it again from Alfio. But again, pick up the media, and the one that's kind of on my mind at the moment because it's in my Google feed is the recent NVIDIA announcement to build a digital twin of the planet. This is great, it's very exciting, but as we go forward, the big data alone, it's not enough, and it never will be enough. So again, I don't think I need to keep briefing this slide because all the talks today really, really touched on this. We absolutely need to be bringing in the physics-based models along with their predictive power, their interpretability, and all the domain knowledge that they possess. So with that kind of as a framing, here are the topics that I'll touch on, and I'll go pretty quickly through the first two and focus mostly on the third one in terms of what are some of the mathematical and computational foundations for digital twins. And again, we've really heard about the first two in several of the talks earlier today. So the first is the notion of physics-based modeling, which I think absolutely has to be baked in there. And maybe in this room, having seen the talks, that's well accepted, but this is a message that absolutely needs to get out to the broader community, that digital twins need physics-based models baked into them. Second, again, as we've heard already from multiple of the talks today, we need reduced order models as a way to make the computational cost tractable for bringing in the physics, and also as this mechanism. I really liked, I think it was Eleni who had the slide, or it might have been Alfio, where we saw reduced order models sitting halfway between the physics-based and the machine learning worlds. And then finally, I'll talk about probabilistic graphical modeling, which is something that we've drawn inspiration from the robotics community, which we've been using as this foundational mathematical framework as a way to integrate data models and decisions. And like I said, I'll go very fast. I really won't go into any detail at all on the first two and spend most of the time on the third one. So again, physics-based models, I think I'm going to zoom over this one because the speakers ahead of me have done a really nice job of framing. But one thing I will say is that over the last few years, as I've given more talks in venues where there's a lot of computer scientists, I've come to appreciate that not everybody understands or knows what we mean when we talk about a physics-based model, or in medicine, a mechanistic-based model, that we keep talking about these things. And I can just remember some very eye-opening discussions with computer scientists where you really get down to what is a physics-based model. Of course, it comes in many shapes and forms, but more often than not, when we're thinking about complex engineering, scientific, and medical systems, it's coming to us in a set of partial differential equations that encode the governing laws of nature, our constitutive relationships, and so on. And again, as we've already heard today, physics-based models are so powerful, and they really bring the predictive capability. They bring the ability to start issuing predictions, often with quantified levels of uncertainty about conditions that we haven't seen in the data, but the catch is that they're computationally expensive. And again, there's kind of two parts to the story here. One is that Apollo reminds us that a digital twin does not necessarily need to go down to the very finest level of detail in order to be useful. But the other is that as we want to use something like a digital twin to drive ever more complex decisions, it's clear that we can't even today simulate some of those phenomena at the scale that is needed. And in particular for a digital twin, what the challenge is that we have to go to the system level, right? We're really talking about getting to the level of a full organ, a full human patient in the medical setting. And so physics-based models are really too expensive to that. And again, just before I leave this slide, one last point is, and again, sorry, I don't know if there's anyone from NVIDIA here today, not to pick on them, but they just had a high-profile keynote and a lot of media around it. A digital twin for the planet is only going to be as good as the models that sit inside it. And we are still far away from being able to create climate models at the resolution needed to truly model the climate at a planet level over the decades or centuries that are needed. We are far away from being able to do that. Digital twin is no magic. It's not going to magically solve that problem for us. So absolutely, as a community, we have to continue to invest in the forward simulation capabilities that, again, let us go down to finer scales and let us simulate more at the system level and over long time horizons. And whether it's aircraft, the climate, or medicine, again, there are so many problems that are still out of reach from the point of view of physics-based simulation. Okay, so computational cost, this is where reduced order modeling came in. And again, Eleni gave us a beautiful tour this morning of the many different kinds of surrogate models that one can use. And again, I see this whole broad category of surrogate models as an absolutely essential enabler for digital twins. In my group, we tend to focus on the projection-based reduced models that Eleni also mentioned. So again, and again, not to go into too much detail because Eleni covered it really nicely, but the setting here is that we have some kind of a high-fidelity physics-based model that we trust, that we consider to be of sufficient high fidelity for the task at hand, but it's too big. Its dimension is very high because it represents discretized partial differential equations often, and it takes too long to solve. And Alfio, I was kind of pleased to hear your example of days for your simulation because one of the applications we're working on right now with the Air Force is rocket combustion, where the forward simulations take weeks. And I mean, it's just sort of mind-boggling how complex these forward simulations are, and just, again, to emphasize the last point, how beyond, how far away it is before we really can have this kind of simulation capability at our hands. We're in a situation with the Air Force right now that we're collecting snapshots to build our reduced models, and we get 10 new snapshots every week because the supercomputers are busy grinding out these solutions. So we have this kind of model that we trust. Again, it's too expensive. So the idea is to try to derive a projection-based reduced model. And what is special about projection-based reduced models is that they really exploit and preserve the structure of the system that you're trying to approximate. So even though this reduction is done mathematically, it's done through methods like the singular value decomposition, methods that are also used in machine learning, it's done in such a way that the physics as manifested by the structure of the original system are really baked into the reduced model. So 3 main steps in reduced modeling. The first one, a training step, solving the governing equations to generate training data. The training data should, of course, be representative of the parameters or the different dynamics that you would like your reduced model to be able to capture. A second step where we identify structure, and here we are looking for low-dimensional structure. For many methods, this low-dimensional structure can be defined by a linear subspace, so defined by a low-dimensional basis. And then third, the really important step, and the step that distinguishes reduced order modeling from machine learning, is this projection step where we go back to the partial differential equations and mathematically project them onto the low-dimensional subspace that was identified in step 2. So this is, of course, not a new topic. Reduced order modeling has seen a considerable amount of development in the last couple decades, to the point now that there are a really powerful set of methods that allow one to create reduced order models of complex systems, and for many, not for all, but for many classes of systems, not just come up with a reduced model, but also come up with an error estimator so that when you're using this cheap approximate model, you have a sense of just how good your predictions are, even outside of the training data. As I already said, I really see reduced order modeling as a key enabler for predictive digital twins. We have to get the physics into the digital twins if we want to be predictive. Reduced order modeling is a way to do that at low cost. You'll see this again when I come to talk about our application, but again, just to highlight, this is the area that we've been working together with Axelos to build reduced order models of a structural model of an unmanned aerial vehicle. Okay, so with those kind of just very brief comments on the first two topics, let me spend the rest of the sort of methods part of the talk talking about probabilistic graphical models. And as I sort of said starting out, I think it's very important to have a strong mathematical foundation for digital twin in order to get away from the every time you create a digital twin of a new system, it's kind of it's a new thing that needs its new implementation. So we're going to do this using probabilistic graphical modeling. And as I already said, this is something that we drew inspiration from the robotics community. And if you really think about all the different domains that are out there, robotics is a field which in many ways has had sort of digital twins for a long time because they often have simulations that are going along with the robot and having that two-way interaction between the physical and the virtual to drive decision making. So in the language of probabilistic graphical models, we're going to start out by creating a formal mathematical abstraction of the digital twin and its physical twin. And to do that, we're going to define 6 elements. The first 3 elements live in the physical space. The first one here is the physical state. So we're going to think very intentionally about what is the physical state of the system that we want to track over time. And so the subscript T here denotes a time index. The observational data, what are all the available information that we have describing the state of the physical asset. And our observational data could include things like sensors on board the vehicle, as well as inspection data, flight logs. So observational data can be coming to us in many different shapes and forms on different spatial scales and on different temporal scales. Then third, we have the decision space. What are the control inputs? What are the decisions I can make or the actions I can take to influence the physical asset? And just like the observations, these controls could happen on board the vehicle. So it could be deflecting a control surface to change the way the vehicle's flying. Or it could be a decision to install a new sensor or a decision to do an inspection, something that will affect the information that I'll get in the future. Then to complete the abstraction, we have 3 quantities that live in the digital space. So you'll note here that we have the digital twin state. So in our mathematical abstraction of the asset twin system, you'll notice that we differentiate, we track separately the physical state and the digital state. And I'll say a little bit more on this when I walk through the example. But this question of what is the digital state is, I think, a very, very important one. And I think it's one that actually is also very open with research challenges. This is where the physics-based models play a critical role, because without the physics-based models, you're kind of stuck with trying to track everything, as opposed to having a powerful model that encodes behavior and then, for example, defining the digital state to be the parameters of those models. This digital state, of course, has to also be fit for purpose, depending on what it is you want to do with your digital twin. What are the things, what are the states of the system that you actually have to track? And of course, it has to balance the fidelity with being computationally tractable. So there's so much sort of buried here in how one abstracts the digital twin and defines a digital state. We also define quantities of interest. These are the quantities that we want to be able to predict, again, with our predictive physics-based models. So given the digital state, what are things like maximum stress, maximum strains, displacements? And then we need to define the notion of a reward. How do we quantify performance, and how do we measure costs? All of that baked into the reward. Okay, so now we have these 6 formal elements. We can start to build a probabilistic graphical model that's going to represent the digital twin and its physical twin. And in the example that I'm going to show you, I'm going to start by building a dynamic Bayesian network. So in this network, in this graph that we're building, here we're looking at the physical state of the system evolving in time. So we're looking at 3 different time instants. And the nodes in the graph here represent random variables. So we're modeling the physical state of the system as a random variable. The edges in the graph encode the relationships between those random variables. Or said another way, the edges are these conditional probabilities where this edge here is describing the transition of the physical state from T1 from T0 to T1. In the digital space, we can similarly draw the part of the graph that corresponds to the evolution of the digital state. So again, we're going to represent the digital state as a random variable. And again, here we're looking at it transitioning in time. Here we have the observations that we make in physical space. And of course, the observations are almost always indirect. We can almost never measure exactly what it is we want to know. The observations are almost always indirect. The observations are almost always noisy, and they are sparse, both in time and in space. And so this physical state is, again, almost never fully observable. It's partially observable at best. Again, the edges in the graph are the conditional probabilities that encode the relationship. So they're telling me what it is that I'm able to observe. And from that, I could solve a familiar inference problem to infer the digital state. I can introduce the actions. So now the actions, which again I take in the physical space. So once I put these decision nodes in, the dynamic Bayesian network becomes a dynamic decision network. I can introduce the quantities of interest. Remember, these are, again, the quantities that I want to predict using my models. And I can introduce the rewards. And again, just keep building up the graph. I can extend the graph into the future. So if I were sitting here at current time 2, then I can make predictions about what I might expect to see or plan optimal actions for the future. And again, keep building out that graph. So this graph now, this probabilistic graphical model, this dynamic decision network that you're seeing here, this is our mathematical model of the digital twin. You can think of it as a graph, or if you prefer, you can think of the mathematical model as being this giant joint probability distribution that, again, represents the relationships among the digital twin states, the quantities of interest, the rewards, the future controls, all conditioned on what we've seen, what we've observed, and conditioned on what we've done in the past. Then once we have now this model of the digital twin, we can start to manipulate it. And in particular, the conditional independence structure that's defined by the graph lets you factor it in different ways, and we're going to factor it into these 5 factors here. So these 5 factors now start to expose all the familiar tasks, all the actually things that we've seen all day. What is it that you need to do with the digital twin? There are computational tasks that relate to the digital state transition. How does the digital twin state transition from where it is at t-1 to where it is at t, conditioned on the action that you take? There are computational tasks that relate to making predictions. Given my estimate of the digital twin state, issue me a prediction about a quantity of interest. There's the part that encodes how the reward function is measured. There's, of course, the inverse problem, the familiar assimilation task. And you see here sort of familiar conditional probabilities here, the likelihood. And then there's the planning or the control, the decision part. So again, there's, at this point, now going to be nothing new in the methods. The methods that we can sit on top of this mathematical model are all of our favorite Bayesian methods that we use for solving inverse problems, for doing prediction forward in time, and for solving planning or control or optimization tasks. But they all now fit in a very integrated way into this framework. And again, you can't see them in the language of the probabilistic graphical model, but the physics-based models, and in particular reduced models, are all here. And in particular, the reduced order models really sit on the edges of the graph. When I say issue a prediction of a quantity of interest, what I'm really saying is run the finite element model to tell me how the airplane wing is going to perform under these different loading conditions. Right? Same thing when I do the assimilation, it's not just learning from data because the data are so inadequate. It's learning from data through the lens of the model via a Bayesian inverse problem. So the physics-based models are all deeply embedded, and I like to think of them as sitting on the edges of the graph. All right, I won't go through all the gory details of all these probability distributions, but the slide is just supposed to, again, give you the sense that representing the digital twin as a probabilistic graphical model is a way to get this integrated framework, and in particular, all the different use cases, so virtual inspections, predictive maintenance, some kind of optimization of operations, or learning from historical data. These all manifest in different ways. They all light up different parts of that graph, or they all manifest as different conditional probability distributions. And again, to emphasize, there's now no innovation needed on the methods themselves. They sit very, very naturally on this framework. Although, of course, we continually need better methods, innovation on the way we solve these problems to let us go to the kind of scale that we need. All right, so for the next part of the talk, I'm going to step really quickly through how we put all this together for the task of creating and then evolving and deploying a structural digital twin for an unmanned aerial vehicle. And as I go through, what I'm going to do is show you how we build the digital twin, and I'll show you how even these calibration steps fit into the probabilistic graphical model setting. So as we go through, we're going to see how the actions, the observations, the quantities of interest, and the reward functions change depending on what it is we're doing. Then when we have a calibrated digital twin, we'll see how we can use it to do dynamic updating in response to changing structural health of the UAV, and then use it to support, in this case, dynamic decision-making in the form of mission replanning. This is the hardware. I should say I am almost exclusively a computational person, but every now and then my projects involve hardware, and this is one. It's been kind of fun. I say I have learned a lot. That's the vehicle at its first flight up in Massachusetts. We also have a benchtop testing setup because we can get a lot more data and a lot better quality data in the lab. The funny story is that, of course, when the vehicle got transported down from Massachusetts to Texas when I moved to Austin and was all nicely set up, and then, of course, when the pandemic hit, the labs got closed. So I packed it up and brought it home, and it's been ever since sitting in my garage at home. And so here's one of my middle schooler recruits. I guess in pandemic times you get a little bit desperate about lab help. That's my son. I'm not sure how thrilled he was to be there operating the scope. But anyway, he also got to learn a little bit about structural sensing. Here's the underlying physics model. So again, finite element structural model. This is the work that we do together with Axelos. Let me go back here. If you can see, this is the internal structure of the wing. So we've set up the finite element model to mimic the structure of the actual wing as best we can. And again, just to sort of give you a sense of the speed ups that the reduced order model gives, the finite element model, here it is. It runs at about a minute of an analysis, which is pretty remarkable, really. But if you need to do many, many, many thousands of analyses in support of decision-making, or if you're flying and you've got a split second to make a decision about whether to turn a corner with your damaged vehicle, clearly this, although impressive, is not fast enough. the reduced order model gives us about 1,000x speed up with really remarkable levels of accuracy. And so this now is getting to the point that you can think about deploying these reduced order models in near real-time settings on UAVs. All right. I want to sort of pause a little bit on this slide and say a little bit about the digital state that we're using. And again, this is the reason I want to go through this in a little bit of detail is because I think this is a really important question that people kind of jump over. People are ready to create their digital twins by integrating models and data. But as I've already said, the question of how you define the digital state is going to affect so much of the algorithms that you sit on top. And it's a fascinating question. What I want to call attention to is in the digital state that we're going to use here, we have 3 different flavors of states. The first are the states that represent the variability from UAV to UAV. And so that is, for example, the geometry and material properties that are different because of the manufacturing process. We also have these structural health parameters. And again, these are going to be different from UAV to UAV depending on how that particular UAV has been flown and how it has or has not been maintained. So those ones are representing that asset-to-asset variability, that personalization of the digital twin. The vector of added point masses here, M, if I go back 2 slides, and it's a little dark, but maybe you can see or maybe you know that an aircraft wing is not a beautiful, clean not a nice sort of clean structure. It's got a whole lot of stuff on it. For example, this is a servo motor that drives the ailerons on the wing. So now you want to create a digital twin. Clearly, the presence of this servo motor affects the structural dynamics of the wing. So you have a choice, which is either you sort of go down the road of a fairly exquisite, detailed finite element model that resolves the servo motors and all the other stuff hanging on the wing, or you do what we did, which is to build a nice, simpler, cleaner structural model, and then include this, what I think of as a model inadequacy term, or in this case, a hardware inadequacy term, parameters that are going to account for the physics that we don't represent in the digital twin. And then the third flavor of parameters here, the Rayleigh damping coefficients, are actually sort of similar in spirit, but now rather than being unmodeled details of the hardware, these are things that are not modeled in the physics. And again, you probably know that this is a very common engineering approach for bringing damping into otherwise inadequate structural models. And again, I'm emphasizing those not because of what we're doing here, but because of this notion of having inadequacy and parameters that represent inadequacy, I think is absolutely essential in the digital twin. And then, of course, all of this is done in a probabilistic setting, so we'll be carrying uncertainty along at every step. And even though the models are known to be imperfect, because of their uncertainty quantification, they're going to be useful in our decision-making. Because everything is Bayesian, we're going to need prior information on all of these parameters. So you can see here the priors that we have. Now we've defined the digital twin state, we're ready to start building the digital twin. So the first step is going to be to calibrate the geometry. We have the prior, which are the plans. I should have said we designed and built the aircraft together with Aurora Flight Sciences. It's quite remarkable how different the as-manufactured vehicle was, how different it was from the plans, or maybe I shouldn't have been surprised by that. Observations, go out and measure the geometry. In this case, because we can measure the geometry very, very accurately, we choose to just represent our posteriors as deterministic quantities, so we don't carry forward uncertainty in the geometry, but certainly we could. Second, we calibrate the material properties. To do this, we apply a load displacement test where we apply a known tip load at the wing. And again, being home in my garage, we had to get kind of creative. There were bottles of water and there were rugby balls involved. And maybe later over the drink session, I can show you some photos of our creative experimental setup. Anyway, we apply these known tip loads, measure the displacement. We can generate these pairs of now forced displacement. Again, everything's Bayesian. We have the prior. The prior is Gaussian. The likelihood is non-Gaussian. So we have to do that update from prior to posterior using a combination of sampling and kernel density estimation and then using a particle filter. So now, again, we've sort of raced through the experiment, the update. We've calibrated the geometry. And what I want to emphasize here is that we have calibrated the material properties for the vehicle that's sitting in my garage. But we haven't calibrated to a deterministic quantity. Rather, we've got this posterior. And we're going to bring our uncertainty in the material properties forward with us. And it's always going to live with the digital twin. So the digital twin is inherently probabilistic. Oh, I pushed it twice. Something, all right, there we go. There we go. Something about that slide was getting hung up. All right, third step is going to be to calibrate those mass and damping factors. Here we do a dynamic test where we do an initial displacement of the wing. We measure the dynamic response. And again, same sort of story, collect the experimental data, a little bit of post-processing, and then come up with these posterior distributions on those mass and Rayleigh damping factors. All right, so now we have a calibrated digital twin. We're ready to thinking about using it in a deployed setting. And the particular example that I'm going to show you, we consider the vehicle flying. While it's flying, it undergoes some damage, or some kind of, the structure gets compromised on the two panels that you see here. We have a whole bunch of wing-mounted sensors that provide very noisy strain data. The idea is to now take the strain measurements, very rapidly do an adaptation of the digital twin, and I'm not going to talk about it today, but for the rapid adaptation, we're actually training optimal classification trees and using those as a way to do the very rapid adaptation, again with the reduced order models, and then use the digital twin to make the decision about whether you can keep flying this aggressive maneuver, which gets through the mission faster, but pulls tighter turns around the corner, so puts more load on the damaged structure, or whether you have to switch to this more conservative maneuver, which takes longer but is gentler on your damaged structure. And just showing you how this comes together, and I should say that this is simulated data. This is all deployment in ROS, the robot operating system, but this is not flight test data. To sort of show how it all comes together, we can, for example, track the digital twin state here, the two structural health parameters. And because this is simulated, we actually know what the ground truth is. Again, I want to emphasize everything is probabilistic. So we're tracking our estimate of the state and our uncertainty. You can see that we're a whole lot more confident about what's going on the inboard panel than we are about what's going on the outboard panel. You could take this kind of uncertainty estimate and use it to make a decision about new sensors that you might need on board. You can see here the strain measurements, the simulated observed strain measurements. We reconstruct estimates of the strain data. This is part of our reward function, relates to how well the digital twin predicts future measurements. You can see here the decisions that are made. We start off flying aggressively. At some point, the damage worsens badly enough that the digital twin says, time to switch to the conservative maneuver. And then here you see the reward functions, which are balancing flying aggressively to complete the mission faster, flying conservatively to preserve the structure, and then a reward function that relates to the accuracy and the adaptation of the digital twin. Okay, so just in the last maybe 3 minutes, I just want to talk about some of the very recent work that we have going on in collaboration with one of the other groups at the Oden Institute. And I realize there are medical experts in the audience, and so I have to be very careful not to say anything wrong about the medical aspects of this, but that's all right. You have to give me a pass since I'm an aerospace engineer. But again, if you think about where I started out, it was we need to start thinking about the mathematical and computational foundations that apply broadly across digital twins. So digital twin of an unmanned aerial vehicle, or digital twin of a cancer patient. What I'm going to show you is that this probabilistic graphical model abstraction and then the computational framework that sits on top of it just has a beautiful sort of rolls right out in the cancer patient setting. And so in particular, if we were to think, and in the example that you'll see here, we'll be thinking about a breast cancer patient. But again, to go back to those 6 elements that I defined, here are the 3 elements in the physical space. The physical state, which needs to be the anatomy of the given patient, the vascular system, the mechanical and the physiological state, both of the tumor and of the underlying patient themselves. The observational data, which again, just like the aircraft example, comes in a lot of different modalities with different spatial resolutions and different temporal resolutions. And then, of course, the control inputs, just like the aircraft example, could be a treatment that is actually directly impacting the system, or it could be decisions to do inspections or to take a biopsy to collect more data in the future. And similarly, the three elements on the digital side, the digital twin state, which we will be using to track the dynamics of the tumor, the spatial extent and its temporal evolution and the mechanics. The quantities of interest, all the things that we would like to be able to predict once we've characterized the state of the patient. And then the reward functions, which relate really to patient outcomes, how effective is a treatment, the toxicity levels, and then, of course, maybe the costs and the intrusion of performing more tests or more imaging. So again, just like everything I said for the aircraft, physics-based models need to sit underneath this, just like we saw with Alfio's heart models. Physics-based models combined with the data all sort of put into this probabilistic graphical modeling setting to build a digital twin. And so again, I'm not going to go through in detail, but I'll say I've got several folks in my group working together with the Center for Computational Oncology that sits in the Oden Institute. That's Tom Yankelov's center. So we've been working with the breast cancer modeling, and then also this example here, this is a glioma, a brain tumor, where again we can start to now build the graphical model. And again, sitting on these edges are physics-based models. We've started off with the simpler ODE-based models just to sort of get everything in place and get them going, but we'll be moving really soon to the full partial differential equations that the Center for Computational Oncology has that really describe the evolution of these tumor properties. So I think this is really exciting, and it's always really amazing. Now I'm going to put my mathematician's hat on, but as a applied mathematician, it's so exciting to have a vastly different application to challenge your methodology, because you start to see now how you exploit the common features, but then also what are some of the elements of the new application that challenge the methods and take them to the next level. So with that, I'm going to close. I do want to close by going through a few challenges. Again, I'm not going to pick on any particular companies in these last closing statements, but if you could listen to some of the companies who are selling digital twin stuff, you could believe it's a solved problem, that all you need to do is go out and buy the right software and hardware and push a button and you can have your digital twin tomorrow. Well, we all know that that's not true. There are so many challenges. And as I said earlier, getting to accessible, robust digital twins at scale is going to take a lot. It's going to take partnerships and software. It's going to take standards. But it's also going to take a lot of investment in the mathematical and computational foundations and the algorithms that make everything I've talked about today possible. So I have here 5 of my favorites. Maybe I'll just really quickly hit them. Predictive modeling. Again, I cannot say enough. Predictive modeling is not a done deal. The community needs to continue investing in predictive modeling. Absolutely. Second, validation, verification, and uncertainty quantification. I've said this several times, but I do not believe digital twins can be deterministic. I think we make a huge mistake if we start standing up beautiful deterministic digital twins. We need uncertainty quantification baked in from the very beginning. Otherwise, we will not be equipped to use these digital twins to drive the most critical decisions. And then, of course, validation and verification are also important partners to all of that. Data models and decisions across multiple scales. You start to see a little bit of that with the aircraft example and certainly with the cancer examples. But how one really, truly integrates across multiple scales, again, I think this is a grand challenge for applied mathematics. Scalable algorithms, everything I talked about today was Bayesian, and of course we know that even the state-of-the-art Bayesian algorithms for data assimilation, for optimal planning under uncertainty, even they start to fall apart when we go to the number of parameters that we're going to need, again, if we truly want to have a digital twin of the planet or a digital twin of a human. And then finally, optimal sensing strategies. Again, I think that one of the things that's so exciting about the digital twin concept is that it's not just data feeding a model, but that there's that two-way interaction so that the models can drive the sensing strategies. And of course, in medicine, this is huge, deciding what tests to run and when, and balancing that with the intrusiveness of testing on a human. I think we're just starting to scratch the surface in terms of the OED, the optimal experimental design, the intelligent adaptive data acquisition, and the integrated sensor design that can enable all of that. So with that, let me stop, and I will be happy to take a few questions. Thank you.
Thanks a lot, Karen, for this great talk. So we have time for questions.
I'm trying very hard to stand on this spot, and it's very hard, I have to say.
Thank you very much for a great presentation. I also very much liked the insistence, or the elaboration on this graph structure. And we were just discussing with Professor Kiritsis, I think he's in the audience, how important it is to have an architecture that can describe digital twins across domains. And I think the graph structure is really fitting for such a purpose, and maybe to use it with ontologies or other types of constructs. I was wondering, what is the potential you see for adaptation on the reduced order models themselves? So, of course, we can train them, and we could claim that we can spend a lot of offline time to do the best we can, but there's going to be areas where we learn from data that maybe we need to go back and adjust them. Is there a strategy to best achieve this goal?
Yeah, absolutely. So this is a critical part. In fact, that's the technical part of the talk I took out to try to stay within time. So I'll tell you what we've done, but again, I think this is certainly an area that needs more attention. So if you look in the literature, there's been a lot of work done on adaptation of reduced models, and there's a variety of different ways you can do it with, for example, low-rank updates and fast adaptation. The approach that we took, because I mentioned we were working with Axelos on the reduced models, and Axelos build the reduced models with a component-based approach. So building reduced order models on the components, and then very cleverly putting those together to create the system-level model. And so, for example, our aircraft wing that you saw there had 15 components on the wing. So the strategy that we use for adaptation was to create a component library where we have multiple copies for each component. So you could imagine, panel number 3 on the wing. We ahead of time have computed reduced order modeling components where it's pristine, 10%, 20%, varying levels of damage. And all of those are stored in a library. Then the optimal classification trees that I mentioned, we can very rapidly take the data, classify which state we're in, grab the right component from the library, piece it together, and do the reduced order model evaluation. And so I think, can you do it fast enough to make the decision before the airplane has to turn the corner? Well, that's still, I'd say, an open question, but the notion of decomposition of a complex system, updating on the pieces, and then the right kind of mathematical framework to put it back together, I think is a critical enabler. And I think it's going to be one of the critical pieces to get to scale. So that's not to say there are not other approaches, but I think decomposition and component-based updating has got to be a key part.
You have mentioned being able to pass to scale up the system as one of the critical elements in deploying digital twins. And you have presented the fact that having a uniform abstract framework, the Bayesian graphs, for instance, is a key. But there is a practical aspect as well, which will require data sharing. And for that, there may be confidential data or privacy-related data, especially in the health-related applications. Did you already take that on board, or is it something that you have in the future steps?
It is not something that we've taken on board. And when I had the slide that said getting to digital twins at scale requires many things, figuring out this issue of data sharing across many different stakeholders when there are confidentiality issues. And again, not to connect two very different questions, but again, I feel that the notion of decomposition is going to be absolutely essential here. And by the way, this is something that engineers know well, right? This is what engineers have been doing, is that they decompose themselves into working groups and work on different parts of a complex system like an aircraft and then bring it back together. Of course, we also know what the dangers of doing that are, because you make decisions that are locally very good for you, and then when you come back and you have the nonlinear interactions among the pieces, you get into trouble. But from again, even from a mathematical standpoint, and the notion of federation and machine learning, I think is going to have to be essential, because there's going to have to be things that are done locally, either because of the complexity or because of the concerns of not being able to share the data, or both. And this is a great topic for mathematicians, right, to work on. So I do not have an answer to that question, and that's something that we have not taken on. But you're right, it's absolutely key.
There was a question over there.
Thank you. We saw a lot of examples today about physical state and simulation of physical states. What are your thoughts about behavioral digital twin when we simulate the behavior of a person?
Yes, this is a great question. I have the 5 challenges that I showed on the second to last slide. I have another version of that one where the 5th challenge is how do digital twins interact with human decision makers. And again, I think this is a big challenge and a big open question. I think, to my knowledge, this is something that people have only just started to think about, and I'm not aware of a whole lot of work in the area, but it's everywhere. So, for example, the US Space Force, which was just recently stood up as a part of the US Air Force, is very interested in digital twins for tracking objects in space, right? Because in orbit, we're sort of in a looming disaster with the number of assets that are up there, all put up by different countries. Nobody knows what's where. Nobody's telling anybody else what's where. And so using digital twins for that. But a really key part of that is, how do those digital twins interact with the human decision makers that are actually the ones making the decisions on the ground? And should the human be a node in the probabilistic graphical model, so that you represent the RAND? I always laugh when I think about that, because I wonder what Fabio's. I think my distribution would be a little bit wider than Fabio's, but anyway. But should we be modeling the human? We have in some way. So there's the effects of the human on the system and how the digital twin has to account for that. But then there's also the part of, how does a digital twin communicate information to a human decision maker, which is probably going to be one of its tasks, in addition to maybe some kind of automated sensing. So it's a great, great question. And again, to me, this is one of the big open areas as digital twins start to move into some of these more complex societal problems.
Thank you for the very wonderful presentation. And I have a question regarding the graphical model. So I just want to ask if the model is very robust, like if you kind of adjust when you calibrate the material parameters or other parameters, is it does it give you some wildly different result, or how can you assess like your model is robust enough or not? Do you have any ideas?
Yeah, it's a good question. So, I want to repeat something I said earlier, which is, there is no magic. There is no magic in digital twins, despite what some people might hope for. However you build your digital twin, and let's say we use the probabilistic graphical modeling formalism, it's only going to be as good as the models and the data that you have in there. And so your question about the robustness and the sensitivity, well, how well can you estimate the digital twin state given the observations you have? And of course the answer is it depends, right? It depends on the complexity of the dynamics, it depends on the sparsity of the observation, it depends on the noise. So of course the Bayesian modeling paradigm is imperfect, because you have to come up with a prior, and if you don't have good priors, then you're not going to get good posteriors. I do feel that the Bayesian way of modeling things, more than anything else, gives you a sense of when you could be in real trouble. But again, there's no magic. There's no getting away from what you can predict with a regular old model. The digital twin is not going to do better than that. So, I think that's really the gist of your question. But you know, the question of robustness and sensitivity analysis, these are absolutely critical questions, and we have new opportunities via those feedback loops that I was talking about. And maybe you noticed in the reward functions at the bottom, we had a reward function for error. We're constantly monitoring what the digital twin predicted for the strain measurements that were coming in the future. So we're factoring that in in a way we're kind of monitoring our own digital twin. And again, there's no fix if things start to go wrong, but I sometimes feel like it's better to at least know that things are going wrong rather than just ignoring it altogether. So this is a great question, but it's a question that almost doesn't have an answer. Yeah.
Okay, is there any more question? Well, yes.
If I may, a small one, maybe a stupid one, but if I see a digital twin of an aircraft, I think automatically of what about the certification to get an aircraft equipped with that in the future? Do you have any exchanges with the US authorities on that?
We've had some exchanges, and you know, again, this is a very difficult question. And by the way, the question of certification by simulation has been on the table even before digital twins have become so popular. So let me not quite answer the question about certification, but let me say something else that goes along the lines of your question, which is designing something like an aircraft, right? Designing a complex engineering system. We have amazing simulation tools, but those simulation tools don't design these complex systems. Right? There are teams of thousands of people design these complex systems, and within those teams there are experiments at small scale, experiments at the subsystem and system level, all the way to flight tests, and then there are simulations, and again simulations at component level, all the way up to the full, and then there are processes. Right? Engineering is a process, and so just like CFD did not replace wind tunnels and did not replace that full process of designing an aircraft wing, but rather became a valuable tool that let Boeing and Airbus design better airplanes with incredible efficiency and fuel performance. I think in many ways the digital twin technology is going to be similar. It's not going to replace, and so it doesn't have to stand alone. And it goes back then to this question about the behavioral aspects and the integrations with humans. I don't think yet we've spent enough time thinking about how digital twins becomes yet another, a powerful and a more integrative, but yet another decision-making tool in the processes that we have. And so when it comes to certification, again, I feel like there's existing process that goes beyond, it's not just one thing. And asking the question, how does the digital twin play into it, so that maybe we do it better or faster or cheaper, but not necessarily all with the digital twin. But it's a very complex issue.
Okay, thank you. I think we can close this session, and thank again Karen for this great talk. So this concludes this first day. You are all welcome to join the apéro and the poster session now. And tomorrow we will have the second day, which is more on the industrial perspective. So the opening is at 9, and first talk will be at 9:30. Same place.